Hello everyone. In this video, we're going to be talking about problem A3 from the 2023 USA Physics Olympiad. So this problem centers around phase transitions and basically calculating the coexistence curve of the transition between solid water and liquid water. So you may have seen a diagram that looks something like this before. This is a phase diagram, and you can see that it shows basically the phase of a substance, in this case water, at a given temperature and pressure. So for example, if you take a temperature around 20 degrees Celsius and something around atmospheric pressure like 100 kilopascals, then you're going to get this region, which is liquid. So basically at somewhere around 20 degrees Celsius and atmospheric pressure, water is a liquid, which you should expect. And you can also see that there are these lines that show the boundary between two phases. And these are the coexistence curves. They basically show the lines along which like water can exist as both, for example, a solid and liquid here, or a liquid and a gas, or a solid and a gas. And notably, they all intersect at this point here, which is called the triple point of water. And this is a point where water can exist simultaneously in all three of its phases. And this is somewhere around 0.01 degrees Celsius. So this problem says to consider a heat engine built around the freezing and melting of water. So we're basically going to be dealing with this coexistence curve here between solid and liquid water. And it says that the freezing and melting occurs at a pressure-dependent temperature Tc evaluated at P. And this basically tells us that we're going to be dealing with this coexistence curve where Tc of P tells us the melting point at at pressure P. And so it basically gives us the equation of this line on the pressure temperature diagram, phase diagram. And it says initially we have a volume V of water squeezed underneath a piston so that it experiences a total pressure P1, and the water is on the edge of freezing with temperature Tc at P1. So the steps of the engine are depicted here, and it says the engine then undergoes four reversible steps. In step one, the mass is slowly placed on a piston, raising the total pressure to P2. So this basically raises the pressure of the system without changing the temperature. And at step two, water is cooled to temperature Tc at P2 and frozen. And in this step, the volume of the system is actually going to change because ice is less dense than water. So as we freeze the substance, which is water, we're going to have the substance expand. And so this is why in step two, it looks like there's more volume here than step one. So then in step three, we have the mass slowly removed from the piston, lowering the pressure back to P1. And this, once again, similarly to step one, just changes the pressure without changing the temperature. And then finally, in step four, the ice is heated back to temperature Tc at P1 and then melted. So you can see that since ice is less than water, melting the ice is going to correspond to a decrease in volume, and that's why there's less volume here than here. So the problem then says that assume that water and ice are incompressible with fixed densities rho W and rho I. So part one asks us, what is the net work done by this engine in terms of the two pressures, the volume, and the densities? And in order to calculate the net work done by this engine over an entire cycle, we're going to have to figure out which steps that work is actually being done in. So in step one, we're just changing the total pressure to P2. And since we assume that water is incompressible, this is not going to lead to a change in volume. And since the work done by a system is its pressure P times change in volume dV, this is going to lead to dV equals 0, and that means that there's no work done in step one. In step two, the water is cooled and then frozen to ice. So that means that the volume is going to increase. And so there is work done here. And since the substance is expanding, it's doing work on its surroundings. And that means that this engine is doing positive work in step two. Now in step three, it's similar to step one. where we're just changing the pressure. And since ice is also incompressible by this assumption, there's going to be no change in volume and therefore no work. Now in step 4, we're heating the ice to a higher temperature and then melting it. And here we're going to have a decrease in volume. So basically the system is getting compressed, and that means that work is being done on the engine instead of the engine doing work on its surroundings. And that means that the work done by the engine here is going to be negative. So the total work is only going to consist of the work from step 2 and the work from step 4. So we just have to calculate these two works and add them. Well, the work in step 2, we can say is, since everything is done at this constant pressure P2, it's just going to be P2 times the change in volume at step 2. And we know that the final volume is the volume of the ice, and the initial volume is the volume of water. And since the mass of the system is going to stay constant throughout the entire cycle, we know that the mass is equal to the density of the water times the volume of the water, which is given. We can also write this as the density of ice times the volume of the ice, which we can call V prime. And this means that V prime is equal to rho W divided by rho I times V. So the final volume is V prime, and the initial volume is V. And substituting in this expression, we can get the work in step 2 is just P2 times this factor rho W over rho I minus 1 times the volume that we're given. And we can do something similar in step 4, where everything is instead done at this constant pressure P1. But we have a different change in volume here in step 4, because the final volume is actually going to be the volume of the water, which is V, and the initial volume is now V prime, the volume of the ice. So since we're basically going from here to here, and this means that this is actually going to be negative work as expected here, since the system is getting compressed and therefore it is doing negative work and the surroundings are doing positive work on the system. So this is as expected. We're going to get a negative value, which is going to be P1 times rho W over rho I minus 1 times the volume that we're given. So now we have W2 and W4, and to get the net work over an entire system, over an entire cycle, it's just going to be the sum of these two values, and we get P2 times rho W over rho I minus 1 times V minus P1 times the same factor. And since we have this factor in both terms, we can factor it out and get P2 minus P1 times this times V. And that's the answer to part 1. Now we can move on to part 2. It says, assume the latent heat per unit mass L to melt ice is large so that freezing and melting account for essentially all the heat transfer in the cycle. And we want to find the efficiency of the engine in terms of the two pressures, the latent heat and the densities. So there's a reason why we're assuming that the latent heat per unit mass L is very large, and it's because the latent heat does not actually account for all the heat evolved during an entire cycle. And you can see that in, for example, step 2, the water is first cooled from Tc at P1 to Tc at P2 and then frozen. So that means that heat has to be removed in order to cool the water from Tc at P1 to Tc at P2. And then latent heat has to be removed in order to freeze the water. So what we're basically assuming is that the latent heat is so large that we can basically neglect all the heat required to change the temperature and only look at the heat that's being removed in order to freeze the water. And similarly, in step 4, the ice is being heated from Tc at P2 to Tc at P1, and then it's melted. So heat is actually going to have to be supplied in order to change the temperature between Tc at P2 and Tc at P1, and then more latent heat is going to have to be supplied in order to melt the ice. And once again, by this assumption, we can basically neglect the heat that's added in order to raise the temperature and only look at the heat that's required to actually melt the ice. And this is a valid assumption because if you search up the values, then you can see that the specific heat of water, which we're going to use when calculating heat to change temperature, is on the order of 10 to the 3 joules per kilograms degrees Celsius, whereas the latent heat of fusion, which describes the latent heat required to melt or freeze ice, that is on the order of 10 to the 5 joules per kilogram. And this basically means that as long as the change in temperature we're concerned with, delta T, that's associated with the transition between TC at P2 and TC at P1 is much less than about, let's say, 10 to the 2 degrees Celsius, then we can safely neglect the heat required to change the temperature. And if you read ahead a bit, actually in step 3, we're going to make the assumption where P1 and P2 are very close, and that means that the function Tc evaluated at those two pressures is going to give two very close values as well. So that means that the delta T between P1 and P2 is going to be very small, and this assumption is valid. So how do we calculate the efficiency of this heat engine? Well, by definition, the efficiency of a heat engine is the net work done over a cycle over the heat added during that cycle. And there's a difference between the word net and like total heat, because when calculating efficiency, we don't account for the heat that's actually being removed from the system in a certain step. So in this specific case, in step 2, water is cooled and then frozen. So that means that we're going to have to remove heat from the system. Whereas in step 4, the ice is heated and then melted. And in step 4, that means that we're going to have to add heat. So this term Qin, only the total heat that we're talking about only includes heat in steps where we're adding heat and not in steps where we're removing heat. So that means Qin only includes heat from step 4 and not from step 2. Whereas when we're talking about like a net quantity, like net heat, then we would include both step 2 and step 4 to calculate like the total heat over an entire cycle. And then when we're talking about net work, we're going to be accounting for both the work done in step 1 and step 4, even though one of them is negative and one of them is positive. So there's a difference between the net heat over an entire cycle and then just the value of Qin, the total heat added in that cycle. So we already know the value of the net work over an entire cycle. We calculate that in step 1, but now we have to find the value of Qin. So as said before, Qin only accounts for the heat added to the system, which is in step 4. And once again, we're making this assumption where the latent heat is so large that we can neglect all the heat required to change the temperature between Tc at P2 and Tc at P1. So this Q4 is just going to include the latent heat, and that's just the mass of the system times the latent heat per unit mass. And we can write the mass of the system as the density of the water times volume of the water times latent heat per unit mass. And you can also write the mass as the density of the ice times V prime, which we define as the volume of the ice, but we have to write our answer, like we have to be consistent and not use our defined variables. So we're gonna have to use a conversion where V prime is equal to rho water over rho ice times V anyway, and then that's gonna cancel out the denominator, and we're gonna end up with this same term. So this is the heat Qin. So the efficiency is just gonna be the value of the work, which is P2 minus P1 times this quantity here, times the volume of the water, divided by the heat in, which is rho WVL. And you can see that conveniently, the volume actually cancels out. And this tells us that the efficiency of this heat engine does not depend on how much substance we use. So if you double the amount of volume that's involved, then it's still going to have the same efficiency. So we can simplify this efficiency to P2 minus P1 over the latent heat times this term involving the densities, 1 over rho I minus 1 over rho W. And that's the answer to part 2. So now in part 3, we're making a further assumption that since we assume that all heat transfer occurs during melting or freezing, this cycle has the same efficiency as a Carnot cycle in a limit where P1 and P2 are very close, use this surfactant for an expression for dTc over dP in terms of Tc, L, and the densities. So we're basically assuming that the two pressures involved are actually very close. And in turn, that means that we're working between two very similar values of Tc at P1 and Tc at P2. And it also says that we're assuming that in this specific limit, the heat engine we're concerned with is going to be reversible and reduced to just a Carnot efficiency. So this means that we can equate the Carnot efficiency with the efficiency that we found in part 2. But first we have to quantify the assumptions that we're making where P1 and P2 are very close. That means that we can assume that P1 is approximately P2, and we can say that this common value is going to be some pressure P. And we also have to involve dP into this equation. So we can say that P2 is equal to P1 plus dP. And further, this assumption tells us that Tc at P1 is approximately Tc at P2. And we can say that this common value is going to be Tc, since we're going to want the answer in terms of Tc. And once again, we're going to want to involve dTc as well. So we can say that Tc at P2 is going to equal to Tc at P1 plus dTc. Now, we want to be consistent in that we define dP as the difference between P2 and P1, and dTc as the difference between this function evaluated at P2 and evaluated at P1. So we avoid any sign errors. So now that we have all these conventions set up, we can start finding the Carnot efficiency. So the Carnot efficiency from the laws of thermodynamics is 1 minus the colder temperature reservoir over the temperature of the hotter reservoir. And so now we have to figure out which, because we're basically assuming that in this limit, the heat engine we were dealing with in parts 1 and 2 reduces to basically a reversible heat engine running between temperature reservoirs Tc at P1 and Tc at P2, since those are temperatures where heat is exchanged. And it says that in step 2, the water is cooled from Tc at P1 initially to Tc at P2. So that means that Tc at P2 is actually a lower temperature. And this means that our efficiency is Tc at P2 over Tc at P1. And it's important to check that Tc at P2 is indeed a lower temperature, because if you were to reverse the roles of Tc at P2 and Tc at P1, then we would get a sign error, and that's not good. So if we make a common denominator, this is Tc at P1 minus Tc at P2 divided by Tc at P1. And now from our assumptions, we know that we can write the numerator as just negative dTc, and the denominator Tc at P1 is just approximately the common value Tc. So this is the approximate value of the Carnot efficiency in the limit where the two temperature reservoirs are very close in temperature. And now the problem says, by the assumption of the problem where the heat engine that we dealt with in parts 1 and 2 reduces to a reversible engine with Carnot efficiency, we can just set this equal to this efficiency that we found in part 2. And note that we have P2 minus P1 in the numerator, but we don't want our answer with the two infinitesimally separated pressures involved. And instead, we can write this as just dP. So we have dP over L times the term involving the densities. So now this gives us an equation that we can easily solve to find the ratio dTc over dP. And that gives us dTc over dP is equal to negative Tc over L times 1 over rho I minus 1 over rho W. And that gives us the final answer. But we can actually write this in, since we want to look at the phase diagram, which is actually a pressure temperature diagram with pressure on the y-axis. We can write this in a more suggestive form by basically just taking the reciprocal of this, and we get dP over dTc is equal to negative L over Tc times rho W minus rho I over rho W rho I. And in a specific case of water that we're dealing with, we know that latent heat is by definition positive. We know that we're dealing with temperatures in Kelvin, at least in the problem, not in the diagram, but in the problem we're dealing with temperatures in Kelvin. So this is going to be positive. And we also know that density has to be positive, so these two have to be positive. And in the specific case of water, water is more dense than its solid form ice. So that means that rho W is going to be greater than rho I, and that means that this numerator is actually going to be positive as well. And with a negative sign in front, this means that the entire right-hand side of the equation is going to be negative. That means that dP over dTc, which if you look at a pressure temperature diagram, and in this specific case, a phase diagram, the coexistence curve here that we're dealing with is going to have a negative slope. And that's a specific consequence of the fact that water is more dense than ice. And if you look at a substance other than water, where its solid form is more dense than its liquid form, which is more common, then we're going to have a coexistence curve between solid and liquid that actually has positive slope, looks something like this.